Welcome to this quick introduction to my lecture on-chip interconnect and the propagation delay caused by long wires. Modern technology is packed with many long, skinny wires. Wires, like this one in the middle, have capacitances along its sidewalls to neighbors in the same layer, along its top side to neighbors above, and along its bottom to neighbors below. Wire capacitance is strongly dependent on the width of the wire and on the spacing to sideway neighbors. The bottom part of the graph, the dashed part, is for an isolated wire with no wiring on top and no wiring below. Now we can see that the wire capacitance depends more on the spacing than on the wire width, indicating that the sidewall capacitances are not non-negligible. The resistance of long skinny wires cannot be neglected. At one point, technology changed from aluminum wires, aluminum being the workhorse metal for decades, to copper wires with about half the resistivity to cope with problems of increasing wire delays. This was a milestone development. Now let's have a look at this problem, where an inverter is driving an identical inverter across a long skinny wire with resistance Rw and capacitance Cw. Both the capacitance and the resistance of the wire, they are distributed along the wire. Hence wire models needs at least two circuit nodes. A simple distributed RC model for the wire is the pi model. In the pi model, we have placed half the wire capacitance on each side of the wire resistance. So we have half of the wire capacitance to this node and half of the wire capacitance to the output node. Now also introduce the RC models for the driver inverter with an effective resistance and a parasitic output capacitance, and the receiver inverter, it has an input capacitance C. The general solution for the output voltage is a sum of two decaying exponentials with time constants tau1 and tau2. But how is the propagation delay related to tau1 and tau2? It's not immediately obvious. But most often, one time constant is dominant. Then there is a good approximation using the Elmore time constant being the sum of the two, and replace the two exponentials with one single exponential. This time constant, as I just said, is known as the Elmore time constant. It's after Bill Elmore, who was the one who developed this delay model under the assumption of a dominating time constant. How to obtain the Elmore time constant from the circuit schematic is the next problem. But there is a simple rule for that. Multiply each resistance by its downstream capacitance. So let's have a look at one resistance at a time, starting with the driver resistance, the effective resistance of the driver. Multiply it with its downstream capacitances, which is the parasitic output capacitance, the wire capacitance, and the input capacitance of the receiver. Then we have the first part of the Elmore constant. Then we take the wire resistance and multiply with its downstream capacitance. So we get the rest here. And it can be rewritten so that we can identify what is related to the FO1 delay with no wire. And we have RWCW divided by 2 being the wire flight time. Next step, we obtain the normalized delay by dividing the Elmore time constant by the inverter RC. So we get the normalized delay. We have the FO1 delay as the parasitic delay of the inverter plus the electrical effort 1. And then we have two places here. We see that the relationship, the ratio between the RC product of the wire and the inverter appears both here and there. So I found it convenient to introduce the concept of wire effort, the same way as we previously had logical effort as the ratio between two RC products. Now the wire effort is the ratio between the wire RC product and the inverter RC product. And then we can rewrite the normalized delay. We have the F1 delay and we have the wire effort appearing twice in this expression. Minimum delay can easily be obtained if we optimize the driver inverter to the wire by taking the derivative of this expression with respect to the effective resistance R, and then we obtain an optimal driver resistance being equal to the wire resistance divided by the wire effort. Having developed Elmore delay model for modeling the delay of long skinny wires, let's change our attention to the problem of repeater insertion. For long wires, delay increase as length squared. So the RC product of a wire is equal to RCL squared, where R is the resistance per unit length and C is the capacitance per unit length. So we want to keep wires short. But if we then have long wires, we can divide long wires into segments by inserting repeaters. And by repeaters, I just mean inverters that are identical to the original driver. So if we divide a long wire into M segments by inserting repeaters, as illustrated here below, where we have each segment have a resistance Rw divided by M, Cw divided by M, and its wire effort is the original wire effort divided by M squared. We can get the normalized delay by adding the delays of the M segments. So we take the delay of one segment. So we have the F1 delay of the inverter as if there were no wire. The wire resistance is Rw divided by M appeared twice. The wire effort is the original one divided by M squared, also appears twice. From this, we can take the derivative with respect to M and find the optimal number of segments given by this expression, the square root of the wire effort divided by 2, assuming a parasitic inverter delay equal to 1. The previous inverter sizing is still optimal since the two middle terms highlighted here multiplied with M, yielding the relationship between the optimal driver resistance and the wire resistance, it's independent of M. We can also derive an expression for the critical wire length for repeater insertion, the L crit. Take the wire length and divide it by the optimal number of segments. It can be rewritten as 2L divided by the square root out of wire effort, or 2 times the RC product of the inverter, and they are divided by the RC product per unit area of the wire. And the third topic is how to handle wires with branches. How to get the Elmore time constant when there are branches to the wire. First, we have to add the branching node. Then we have to insert wire pi models. So this is for the first half of the wire and the second half of the wire, and here is for the branch. But for the branch we can neglect or forget about its wire resistance. So neglect branch resistance. We apply a divide and conquer approach to solve the problem of getting the Elmore time constant by attacking the main path first. So we take the driving resistance here, multiply with downstream capacitance, the same as before. Then we take the first half of the wire, multiply with its downstream capacitance, and the second half of the wire multiplied by its downstream capacitance. Of course, we get the same expression as before. Splitting the wire into two models doesn't change the result. Then we take a look at the branch capacitances, and we identify their upstream resistance. So the branch capacitance times upstream resistance. So we have branch capacitance plus the second load times the upstream resistance. So we get the contribution to the Elmore time constant from the branch. And then we can add these two to get the total expression. And we can identify the first part, the FO2 delay, as if there were no wire, and the wire flight time, and these cross terms that involves both the R, CW, RW, and C. So in summary, modern technology chips are packed with many long skinny wires. Resistance of long skinny wires cannot be neglected. Use copper wires with half the resistivity of aluminum wires, and wire models need at least 2 circuit nodes. We have talked about the RC pi model, assumed the existence of a dominant time constant equal to the sum of all time constants, and this is the Elmore time constant, as I said, after Bill Elmore, who developed the theory. The Elmore time constant is obtained by multiplying each resistor by its downstream capacitance. Actually, it can also be obtained by taking each capacitance and multiply it with its upstream resistance. Inserting repeaters to drive shorter segments of the wire that will minimize the delay of long skinny wires. Otherwise, the length increases L squared. And we have learned how to handle wires with branches. Thank you very much for listening.